In section 4.2, we will look at some applications and modeling of quadratic functions. Our first few examples will deal with projectiles. We can track the height of a projectile that's launched into the air with a quadratic equation. Now let's look at what projectiles do in terms of their height. When a projectile is initially launched into the air, it does so at an initial velocity or speed. As the projectile travels up, it begins to slow down because of air resistance and other factors until it reaches a maximum height. That maximum height is the vertex of that parabolic path. Then the projectile starts making its way down toward the ground at increasing speeds until it finally reaches the ground. That means that the path of a projectile follows a quadratic equation which can be written in either vertex or standard form. In this case, we will model such an equation as the function h for height, where the input is t for time. In general, this equation has the following formula. It's negative 16 times t squared plus the initial velocity, which we'll label as v sub 0 times t, plus the initial height, which we'll label as h sub 0. We see the equation here in our first example as well. Now let's look at the first example and figure out how we can use this quadratic formula to answer questions about the height of a projectile. A toy rocket is shot vertically into the air from a 3-foot tall launching pad with an initial velocity of 88 feet per second. Suppose the height of the rocket in feet per t seconds after being launched can be modeled by the function h of t equals negative 16 t squared plus v sub naught t plus h sub naught, where v sub naught is the initial velocity of the rocket and h sub naught is the initial height of the rocket. The question is, how long will it take for the rocket to reach its maximum height? That question is asking for the value of t. Secondly, what is the maximum height? Here, we're going to have to substitute the found value of t into the quadratic function to find the corresponding height or y value. So in this example, we have h of t is equal to negative 16t squared plus 88 times t, because the initial velocity was 88 feet per second, plus 3, because that is the height of the launching pad. So that is the initial height of the rocket. Because this is a quadratic equation where the leading coefficient is negative, we know that its graph will be a parabola that opens down. Remember, the parabola is representing time compared to the height. So in other words, the x-axis is time and the y-axis is height. The maximum height, therefore, is going to be achieved at the vertex. And that's going to be the value of y. So let's find the x value of the vertex, and we'll call that t. According to what we learned in the previous section, the x-coordinate for the vertex of a parabola will be negative b over 2a, or in this case, negative 88 over 2 times negative 16. You can use a calculator or simplify manually. Let's see, 88 divided by 2 times 16, we get 2.75 seconds. So 2.75 seconds after the toy rocket is launched into the air, it will reach its maximum height. But what is that maximum height? Well, we're going to have to find the corresponding y-coordinate for t, so that's h of t. Or in this case, h evaluated at 2.75. So that's negative 16 times 2.75 squared plus 88 times 2.75, and then plus 3. So let's go ahead and calculate that. I've got my calculator here. So that's going to be negative 121 plus 242 plus 3, or finally 124 feet. So this toy rocket is going to reach its maximum height 2.75 seconds after it is launched, and it will achieve a maximum height of 124 feet. Let's look at a similar example. An object is launched vertically in the air at 41.65 meters per second from a 7-meter tall platform. Using the projectile motion model, determine how long it will take for the object to reach its maximum height, and then determine its maximum height. So here we know that the initial velocity is 41.65 meters per second. So we will use that as the value of v sub naught in our equation. We also know that the initial height is 7 feet because that is the height of the launching pad. Now, we recall that this is going to have the graph of a parabola that opens down, where our x variable represents time and our y variable represents height. So again, that maximum height is going to be achieved at the vertex. First, let's solve for how long it takes to reach that maximum height. That happens at negative b over 2a for t, or in this case, negative 41.65 divided by 2 times negative 16. Let's find out what that is. I got approximately 1.3. It's a pretty long decimal, but 1.3 is a pretty good approximation. So at about 1.3 seconds after this projectile is sent into the air, it will reach its maximum height. Now the maximum height will be determined by h of t, where t now we know is 1.3. So let's substitute that in. All right, let's see what we get. 1.3 squared times 16 is about negative 27. It is a decimal, but I'm going to round here to negative 27. And then 41.65 times 1.3 is a little bit more than 54. I'm going to round to 54. And then if we add 7, we see that we get approximately 34 feet. I'm sorry, in this case, we're talking about meters. So let's make sure that we get the right units. So about 1.3 seconds after this object is launched into the air, it will reach its maximum height, and the maximum height will be 34 meters. Now let's look at a different type of application of these quadratic functions. A farmer has 1,900 feet of fencing available to enclose a rectangular area bordering a river. If no fencing is required along the river, find the dimensions of the fence that will maximize the area, and then find what that maximum area is. So there's a lot to unpack here, but a simple diagram should be able to help us. First, we're told that this is a rectangular area and that it borders a river. So I'm going to draw 3 sides of a rectangle. That's where the fence would need to go. And then I'm going to draw the 4th side as being surrounded by water for the river. No fence will be required there. Now we're told that we have 1,900 feet of fencing to be able to enclose the other 3 sides of the rectangle. Now let's assign it some dimensions. Let's say, for instance, that this side measures x units. Of course, opposite sides are the same length, so this one must also be x. Because we have 1,900 feet total available for all 3 sides of the fencing, this 3rd side must be what's left over from 1,900 once we subtract out the 2 other sides. So in other words, 1,900 minus x again will give us 1,900 minus 2x for the length at the very top. Now the area of a rectangle is what we're trying to maximize. So let's use the capital letter A for the name of the function and say that A of x, the area, must be length times width, or x times 1900 minus 2x. In other words, the area of a rectangle is length times width, or in this case, x times 1900 minus 2x. And we're asked to maximize this area. Well, if we look at the graph of the area, it looks like it's going to have a quadratic form. Let's make that a little bit more clear. If I were to distribute the x here, I would get 1900x minus 2x squared. And let me go ahead and write the negative 2x squared first so that it's crystal clear that this is a quadratic function. So the area of this rectangular region is going to have a graph that is a parabola that opens down. I know that because the leading coefficient is negative. And here, the x-axis is going to represent the width of the region, and the y-axis is going to represent the area. Width here is going to be in terms of x, by the way. So the maximum area is going to occur at the vertex. So what does x have to be at the maximum area? X is going to equal negative b over 2a, or in this case, negative 1900 over 2 times negative 2. And let's go ahead and calculate that. We get 475. So when x is 475, we'll get the maximum area for this rectangular region. But what is that maximum area? So that's going to be a of x, or in this case, a at 475 for x. So that's going to be negative 2 times 475 squared plus 1900 times 475. I'm going to use my calculator for this to find that maximum area. These are going to be very big numbers. So I get negative 451, 250 plus 900 and 2,500. So the maximum area, once I add these together, will be 451,250 feet. Now here is a similar problem, but it is going to have one significant difference. Here we have a rancher that has 4,100 feet of fencing available to enclose a rectangular area bordering a river. So far, it seems like everything is the same as the previous example. Here's the difference though. He wants to separate his cows and horses by dividing the region or the enclosure into 2 equal areas. If no fencing is required along the river, we are to find the length of the center partition that will yield the maximum area. So the diagram for this scenario is almost the same. We still have a rectangular area bordering a river that doesn't need a fence, but in this case, we need to add a partition in the middle such that the rectangular area is divided into 2 equal parts. That's going to require some fencing. So not only will we need fencing here and here, but we'll also need it for the center partition. And all of these are going to be equal length. Now we have 4,100 feet of fencing available for the 3 sides of the rectangle plus the partition in the middle. So at the very top, we'll have 4,100 minus the 3 x's that we've already used up. Similar question, we want to find the value of x that maximizes the area, and then we want to find what that area is. Actually, this question doesn't ask that second question. It just wants us to find the length of the center partition that maximizes the area. It's not asking for what the maximum area is, although that's pretty easy to calculate. So the area is going to be, in this case, length times width. And let's write this as 4100 times x minus 3x squared, or even better, let's write it as negative 3x squared plus 4100x. We know that the graph of this area is going to be a parabola that opens down because the leading coefficient is negative, and we know that the maximum area is going to occur at the vertex. So where does the maximum area occur? X will be equal to negative b over 2a, or in this case, negative 4100 over 2 times negative 3. And if we do this on the calculator, we don't get a whole number this time. We get 683 1/3 feet. Now you can write that as a mixed number, as an improper fraction, or as a decimal that is rounded. I've already checked here my math lab questions, and none of them involve decimals or fractions. So you will have less trouble deciding what to enter as a correct answer once you get to those my math lab problems. But in this case, the maximum area will be achieved when the two sides of the rectangle and its middle partition are each 683 1/3 feet.